All right, let's go over this homework. So can you answer the question first off just by knowing what you know? Just from everyday life, which one of these is going to take more energy?
Vaporizing.
The vaporizing. Definitely, it takes a lot more energy to boil water than it is to just melt an ice cube. Okay, so we just know that, but can you calculate that out? How do you know what the actual difference is? This melting, if you look, the H is equal to 80 calories per gram, and the H for vaporization is 540 calories per gram. So you got those, you could look those numbers up online, but they were on the last page of the notes. So the H stands for enthalpy, and that's basically the amount of energy needed to do something, and in this case, change a phase. And so it's 800 calories to melt the 10 grams of ice, and it's 5,400 calories to vaporize that ice. So significantly more. How much more? So this 80 calories per gram, and then it was 10 grams. So there's our 800 number. And then we had 540 calories per gram, and another 10 grams, so the grams cancel, and I get 5,400 calories. If I subtract off 800 calories from that, I get 4,600 calories, so 4,600 would be your answer. Are we okay with that? Okay. So this next question is kind of long, but it shouldn't be very hard. It used the two different equations, and you have to use them a total of 5 times. So I would like you to kind of think about this little curve here. So with this curve, you've got 5 different spots. You've got this place, this spot, this spot, this spot, and this spot. And each of those things is going to take different amounts of energy. And so which equation do you use on the angular portions? Yep. So I need the specific heat equation because the specific heat has a change in temperature in it. The other equation doesn't have a change in temperature in it, so that's the one that you're going to be using for the flat portions. The equation actually is the thing we just used for the last question. I just multiply the heat of vaporization, or the heat of fusion, which is the going from a solid to a liquid, and then multiply by mass. That's it. All right, so this starts at negative 50 degrees Celsius. So tell me what the change in temperature is for that first portion of this curve.
50.
Yeah, the delta T, or the change in temperature, is final minus initial. And the final temperature for this portion is 0 degrees Celsius, because you're just going to get it up to the point where it starts to melt. And then you subtract off what you started. So it's minus 50. So that's why it becomes 50. And that makes sense. If you had a negative number, you'd end up with a negative calories. And it doesn't make any sense that you take energy out of an ice cube and it gets warmer. So make sure it's obviously a positive value. Alrighty. So I'm just going to call it Q1. All right, so it's how much? 250. So 250 grams, and the specific heat is only 0.5 calories per gram degree C. I hope you saw that. We talked about that last time when we did this calculation. The specific heat for ice and the specific heat for steam is half of what it is for water. And the change in temperature is 50 degrees Celsius. So cancel those and cancel those. And I don't know, what is that? It's got to be like 10,000, 8,000. 250 6250. All right, so tell me exactly what that 6,250 calories is doing to this ice cube.
Warming up the molecules so they're moving enough to that start melting.
Don't use the phrase start melting. It's simply warming up the molecules to get it to zero. But what do we mean by warming up the molecules?
Making them move faster.
That's it. So this energy right here is making the water molecules that are locked in the solid state move faster. So yeah, they're stuck in position, but they're vibrating faster. So at some point, they're going to be vibrating fast enough to break free of each other. So this 6250 is simply making the water molecules vibrate faster. All right, so let's look at, I'll call it Q2. And so it's still, all of these are going to start off with our mass. I mean, that makes sense, right? The mass would totally matter. How much energy does it take to melt a single ice cube out of your ice cube tray compared to an iceberg? More. So the mass is absolutely paramount to the amount of energy needed to do this stuff. So I've got a mass, and I'm going to melt this stuff. And to melt it, it's 80 calories per gram. So the grams cancel. So I have 20,000 calories to melt. So what would you say specifically this 20,000 calories is being used to do?
Break the intermolecular bonds.
Force.
Or force.
Okay, so that's perfect. We're going to say this is for intermolecular forces, and this is for, are we good with that? The 6250 is making them move more, and the 20,000 is breaking intermolecular forces. All right, so what's this Q3 going to be used for?
Movement again?
Another movement, right? Because I've got an angle, and so what I'm doing is I take the liquid water, that's at what temperature? Starting.
Zero.
0. It just melted. So I just broke the last intermolecular force, but it's still at 0 degrees Celsius. So I'm going to take it all the way up to what temperature? 100. So 100 minus 0, the change in temperature is 100 degrees. All right, so my Q3 is still this 250 grams, and it's 1 calorie per gram degree C, because that's the specific heat for liquid water, and it's 100 degrees this time. So the degrees C cancel and the grams cancel, and I get 25000 calories. All right, so what is this 25,000 calories being used to do?
Move the molecules.
Move them. Move them more. So movement. Alrighty. Let's move on to Q4. So what's happening during Q4?
Breaking forces.
I'm going to be breaking intermolecular forces for sure, and it costs in energy a lot more to break these intermolecular forces. So it's 250 times 540, and I get 135,000 calories being used to break intermolecular forces. All right. And the last piece of this, so we're going to raise the temperature of our steam from 100 degrees Celsius all the way up to 120 degrees Celsius. So it's going to be 250 grams. And then I'm back to that 5 calories per gram degree C. C.
Isn't it?
0.5.
That's what I put. What did I say? 5?
5.
Yeah, sorry. I put the decimal place. There we go. 5. And it's 20 degrees is my change in temp, because I went from 100 up to 120. All right, and so it's 2,500 calories. And what is that 2,500 calories doing? It's simply making the steam, the water molecules in the gaseous phase fly around inside the container faster. That's it. So we wanted to know what the total is. So you just add these guys up. So I got 2,500.
188,
Yeah. 188, 750. Sadly, I think we have 2 sig figs. So this is calories. So my be 190,000 calories. Are we good with that? Okay. So what's the hardest thing to do? What's the most energy intensive?
Vapor.
Breaking all of the intermolecular forces. So yeah, I know that Q1 or Q2 and Q4 are both breaking intermolecular forces, but the Q2 is breaking some of the intermolecular forces, and the Q4 is breaking all of the intermolecular forces. There's a fundamental difference between gas and solid liquid. What's the fundamental difference between gas and solid liquid?
Contact.
Contact. The gas particles are not touching each other. So to make them not touch each other, you have to put enough energy into them to break all of their intermolecular forces. When I melt it, they're still touching each other. So there's still some interaction between the particles. And I haven't broken that. I've only broken the fact that they're in a fixed position. So that first breaking of the intermolecular forces is only enough to just get them so they can roll around on top of each other. But if I wanted to launch them into the air, I need to give a whole heck of a lot more energy. All right, so we want to calculate the molar mass of some unknown gas at this pressure and at this temperature and at these liters, and I got a mass out of this. Great, okay, so I need a molar mass. What units are molar masses? Grams over moles. Great, okay. So I just need to write a railroad track that gives me grams divided by moles, nothing else. So I'm going to go ahead and start off by putting this 62.5 grams right here. And so now I need to put moles in the denominator. So a good way to do that is 0.08206 liters times atmospheres divided by moles times Kelvin. Alrighty. I've accomplished what I wanted to. I have grams in the numerator and I've got moles in the denominator. The problem is I brought some stuff with it, and so I need to get rid of that stuff. So you okay with me putting 3.75 liters in the denominator?
Yeah, because it'll cancel out.
So now my liter value unit is gone. Cool. I need to get rid of my, let's say my Kelvin unit. So let's convert this 273,792K. So I'm going to put 297K in the numerator here so the Kelvin cancels out. Now I just need to deal with that atmosphere unit, and I can do that by putting the atmosphere unit that I've given into the denominator. So this 98.5 kilopascals. But I can't cancel out the atmospheres with the kilopascals. That's okay. I've still got them in the correct position to cancel them out. So what I need to do next is put the unit conversion here. So do we remember what the unit conversion is? Anybody remember what the kilopascal was? Okay, so for every 1 atmosphere, it's 101.325 kilopascals. And so now my atmosphere unit and my kilopascal unit all cancel out in one shot. So you can use the railroad track to do your unit conversions. You don't have to do a side railroad track to convert that 98.5 kilopascals into atmospheres or vice versa. You can just throw it all in the same thing. So what are the only units I have left? I've only got grams over moles. So I've set this up correctly, and as long as I don't do something dumb like type it into my calculator wrong, I should get the right answer. So 62.5 times 0.08206 divided by 3.75 times 297 divided by 98.5 times 101.325. So I got 417.8 grams per mole. Is that what you guys got? Yeah?
But you can only have two, I think, sig figs, right?
Yep, so,
Just round up to 420?
yep, I'd write 420 grams per mole. That's a pretty heavy gas, but okay. I think that was supposed to be a little bit further down. Let me bump this down here. There we go. All right, so I've got some methane gas, temperature Fahrenheit. That's lame. All right, so we might as well just go ahead and knock that Fahrenheit thing out first. What's the unit conversion for that? Anybody remember what that is?
Yeah, it's Fahrenheit minus 32 in parentheses, and divide 5/9.
Multiply 5/9. Okay. All right, so 62.5 minus 32 equals times 5 divided by 9. So super important that that after you subtract the 32 in your calculator, you hit equals, or that you parenthesize the two of them. Because if you don't, you're going to end up having 32 times 5 divided by 9, then it'll subtract it off of the 62.5, and that will not be correct. You need to take the 32 off first. And then we'll add 273 to this value, and I'll get, how many sig figs we got? 3? Hello? All right. So 273, and I end up with 289.9 Kelvin. Alrighty. Not that that really mattered, but okay. We could have, doesn't matter. All right, so what am I looking for? I'm looking for a volume, and I've got a volume, and I've got a pressure, and I've got a temperature, and I've got a different pressure, and I've got a different temperature. Because calling it standard conditions, that's telling you that you're at a single atmosphere and that you're at 0 degrees Celsius. Okay, so I'm going to go ahead and throw this 958 liters in the numerator because I want a liter number up there. And I need to think about what just happened to this gas and how that's going to affect its size. So I'm at 781 millimeters of mercury for my pressure, and the pressure changes to 600 or 760 millimeters of mercury. And I know that because 1 atmosphere is equal to 760, and you're not going to have to memorize that. It'll be that box, that table will be on the test, but maybe you just knew it. So that's 760. So what happened to this gas? The pressure went down, so I'm not pushing on the gas as hard, so what is it going to do to its size? It's going to get bigger. So I need to take this and write 781.4 millimeters of mercury and 760 millimeters of mercury in the denominator. That way the pressure units are going to give me a larger liter unit. Because I know that this change in pressure would cause this to get larger. Alrighty, the temperature is at 289, and the temperature is going to fall to 273. So what would that do to the size? It would decrease it. So now I got the opposite effect going on. So I'm going to put my 273 Kelvin up here and my 289.9 Kelvin in the denominator, because that would make this smaller. So 9.58 times 78.1.4 divided by 760 times 273 divided by 289.9. And I'm going to get 1.28 liters. Alrighty. So in this particular condition, the temperature won out, correct? The pressure was trying to make it bigger, the temperature was trying to make it smaller, it got smaller, so the temperature had a bigger impact on it. And I just need to make sure that you are making sure that these are independent of each other. Yep, it got colder, but the pressure got less. Don't let those two things affect each other. Just talk about what you're looking for. All right, so I'm going to do a limiting reagent problem. So I got some lead acetate and I got some magnesium metal. We're going to have to come up with a chemical equation here. So what's my chemical equation?
2PdCH3.
I don't know about that.
We're not
Let's-
gonna do,
Let's not balance it
Oh.
first.
oh, sorry.
Let's check, because I don't think we need the 2 PB, but let's just write up the chemical equation first. So what do you want to write up first?
You do, parentheses, you do C2H3O2.
That's fine.
parentheses, and then there's two of them.
Okay. State?
Plus, oh, state,
We'll wait for it.
okay.
Plus.
Magnesium and
Okay.
over, and it's gonna do a, the replacement, yeah, single replacement. Thank you. So that'll be Mg and same thing.
Okay. You want to guess to the state for that first?
It's gonna be aqueous,
How do you know it's going to be aqueous?
because it's an acetate and it's.
Rule 3.
Yeah.
Okay, great. So how do you know it's wet? Because if it wasn't wet, it would be a solid, because it's an ionic compound. You're correct in assuming that it is wet, but why is it wet?
So reacting.
It can't react otherwise, right?
Yeah.
If I had solid magnesium acetate and I set a piece of magnesium on it, would they react with each other? Maybe the magnesium that's directly touching the magnesium acid or the lead 2 acetate right on top of it, maybe those two would react with each other, but then that would be it. So if I literally needed to make myself some magnesium acetate, what I would want to do is put this lead acetate in water, right? And then it would solubilize because of the acetate, and then I could get them to separate it out. Could you see this possibly being a reaction that you needed to do? Let's say that there was some lead in some water. You okay with that? I don't want lead in water. Okay, so I wanted to get the lead out of the water. So I had some magnesium sitting here and I dumped it into the water. Well, the lead, this was solubilized, right? This aqueous means it's lead with a +2 charge floating around in the water. And if I were to drink that, it would do bad stuff to my nerves. Possibly cause cancer, definitely do other bad things. Okay, so I don't want to drink this. So how do I not drink it? I throw in some magnesium. These two things react with each other. The magnesium goes into solution, the lead comes out of solution, and now the lead is just a piece of lead, an actual lead atom, congregating together with other lead atoms. So what could you do? I could just filter it out. Now I've filtered this water out, and what's in my filter paper? Lead. Now I can just drink the water. So, apocalypse, think about stuff like this. Drinkable water. It's always an issue in all the apocalypse movies, right? Drinkable water. Don't want to drink any lead acetate, that's for sure. Do I need to balance this? Didn't you say 2 PB?
Yeah.
You're okay with it already being balanced, right? Okay, so since the lead has a +2 charge, and we know that because acetates have a -1 charge, and we were told that it was lead with a +2 charge in the question, and magnesium's a group 2 metal, so its charge can only be 2. So they just swap partners with each other. There's no, there's nothing weird happening. What is magnesium doing with its electrons?
It gave 2 up.
It gave 2 to the lead took them, everybody's happy. That's just it, done. And this type of reaction is called a what? This is a single replacement reaction. All right, great. All right, so single replacement reaction. And so what I'm going to do here is now determine what my limiting reagent is. So I'm just going to go to the lead for a product. Are we okay with that? All right, so I'll do 57 grams of magnesium. All right, so for every 1 mole of magnesium, what is it, 20 something or other?
24,305.
So what did this first calculation, this portion, this fraction do for us?
Count your magnesium.
So I know my mass, now I want to count them. All right, so I just counted them up. And so now I want to take my magnesium number and I want to turn that into, tell you how many leads I'm going to make with that. And then for the leads, was it 20 what? 6, 9? Can't read it from here.
207.2.
Grams of lead. Ready? So 57 divided by 20, how about divided by 24.305 times 207.2. All right. So for a 5.9 grams of lead. So what assumption did this first railroad track, this first calculation make?
You have enough to react.
I have enough lead 2 acetate to make this magnesium fully react. So let's find out if that was actually true. So I've got 496 grams of lead 2 acetate. So for every 1 mole PbC2H3O22 grams PbC2H3O22. Somebody have a mass for that? 207.2 plus times 4 plus 15.9994 times 4
Is it like 325?
plus 1.00795 times 6. 3. What did I say 3 and write 2?
I think it's 325.2888.
All right, let's go with 289.
Yeah, 289.
Alrighty. So for every 1 mole of C2C2H3O22, we get 1 mole of Pb. And for every 1 mole Pb, 207.2 grams Pb. Alrighty. So 496 divided by my 325 number times my 207.2. And I get 315. 315 grams of Pb. All right, so which is my limiting reagent? A lead 2 acetate. So what I know right now is there's going to be 315 grams of lead in my container. There's going to be 0 grams of lead 2 acetate. There's going to be some magnesium left over. So let's figure out the rest of this. So I'll do out the magnesium acetate. So 496 grams Pb C2H3O22. Man, that's a lot to write. 1 mole. Is the mass? 142 what?
0.3936.
So 496 divided by the 325 number times 142.3936. And I get 217.12 grams of that. All right, great. I started off with 57 and 496. So 553 grams is what I put into the container. So I need to have 553 grams when I take it out of the container. And I know that 315 grams is my lead. And I know that 217 grams is my magnesium acetate. So what do I got left here? So 553 minus 217 minus 315. So that means I've got 21 grams of leftover stuff. And so that 21 grams of leftover stuff must be the leftover magnesium. So I've got 217 grams of magnesium acetates. I've got 315 grams of lead and 21 grams of magnesium in my container. Good? All right, this last one. Relationship of Boyle's law and between volume and pressure. What's the relationship? Indirect or inverse. One goes up, one goes down. Basically, we're squishing a gas so it gets smaller. Or we're not squishing a gas and it gets bigger. That's it.